three more important rules we want to look at. This one is one that looks familiar, but if you remember, we defined this n as any positive integer, is what we said when we first defined it. But it turns out it works for any real number. Okay, so I can give you an example of if I want to take the derivative of, let's say, the square root of x. We'll see that a lot. Then we can do the following. We can say, well, how does this apply? This is a root, but you might remember whenever we had like an nth root of a number raised to the m power, that was that number raised to the m over n. That is, this is the numerator and this is the denominator. So square root, then it's a second root, and that's a 1. So that's x to the 1/2. And I apply the power rule. Bring down the 1/2. Whoops, bring down 1/2. And then take away a half from the power, which is negative 1/2, which we can then write as 1 over 2x to the 1/2, which is fine, or 1 over 2 root x. Same thing. All right. Product rule. This one's tricky. You're going to be tempted to write the derivative of a product as just f prime times g prime, but that's not true. I'll leave the proof video to follow. What you do is you take the derivative of the first function, multiply it by the second function left alone, and then you take the derivative of you leave the first function alone, multiply by the derivative of the second. For example, if I ask you to take the derivative of, well, let's see. Right now we don't have trig functions yet, so I guess we'll just look at it like this. X squared minus 2x times x cubed. Okay, I would have two options here. Now, most of the time I tell you to distribute, but let's just, since we're still limited to polynomial and rational functions that we could probably combine before we do the product rule, let's just make ourselves do the product rule. We'll see where it's really necessary later when we have functions that we wouldn't be able to multiply together. Okay, for example, like a sine function times this polynomial function. Okay, we just don't have a big variety of functions we've been working with so far, but we'll get there. All right, but let's apply this. Take the derivative of the first function. So if you want, you can really organize yourself. I usually don't do this because once you get more comfortable, you might just be able to write the derivative. What's the derivative of that? 2x minus 2, right? Or you can organize yourself. You can really apply the rule. Derivative of the first one times the second function plus, so you try and remember, the product rule always gets a plus. Leave the first one alone. Multiply by the derivative of that second function. Okay. Oh, I guess I could have done this, the derivative of that second function. But that's my habit. That's why I just usually take them as I go. But if you wanted to do an extra step just to make sure you're organized, let's come up here. I now can take the derivative of that, which is 2x minus 2. And it's multiplied by x cubed. Big plus. And then that's that first function left alone, multiplied by the derivative of the second. And then we do our best to clean it up. Oh, I don't know. Let's just run it through at this point. That's 2x to the fourth minus 2x cubed plus 3x to the fourth minus 6x cubed, which is equivalent to 5x to the fourth minus 8x cubed. Okay, how about these guys? Go ahead and pause, see if you can get them. This is, oops, let me jump back there. Sorry about that. This is f, this is g. All right, or this is the first function, this is the second function. First function, second function. So for a, let's see if you like this way. I'm going to look at my rule again. Differentiate the first. Let's just do it this time. Leave the second alone. And I'll just go ahead and write that as 1/2. Plus, leave that guy alone. And then multiply by the derivative of this one. So that's maybe you want to look at this version because we use the power rule. Bring the 1/2 down, so it's 2 times 1/2 times v, the negative 1/2, take 1 away from that, plus 0. And then you can ask yourself, well, 2 times 1/2 is 1. You could run this through 2v 1/2 plus 2/2, right? V to the first is 3/2 plus 2v plus, and then what's v squared times v to the negative 1, you add your exponents. V squared is, if you want a fraction over 2, it would be 4/2. So v to the 3/2. Okay, and then you can combine these guys. 3v to the 3/2 plus 2v. How about this one? Take the root of this. 3x squared times this thing left alone, x squared plus 4. Big plus. And then the other one, right? Leave this alone. Derivative of this. All right, and then we can simplify. I'll leave that simplify to you. We got to get to the quotient rule here. Now this one, I'll leave the proof in the next video. This one's messy. We're going to be real careful with that. And before, well, let me go ahead and show you a way to remember it another way. If it's like high and low, it's just like a way to kind of remember this if you want. High over low, f over g, numerator, denominator. You can say low d high minus high d low. If you just say that over and over again, it's the denominator times the derivative of the numerator minus the numerator derivative of the denominator, or low d high minus high d low over low squared, the denominator squared. Or officially, with g is your denominator, f your numerator, then it's g times f prime minus f times g prime over g squared. Let's see if we can apply it. Okay, the plot the curve and the tangent line. All right, I guess I'm missing some directions. Find equation of tangent line. So we can always throw that one in there, right? Anytime we're doing derivative stuff, we can always say, oh, let's find the equation of a tangent line at that point. So first we need the derivative. So I go low d high minus high d low over low squared. All right, and then we do some algebra. Do some calculus. Derivative, 2x minus x squared plus 1, 2x. So 1, right? All over. Notice usually I'm not gonna square this denominator out. And then you ask yourself, what can you do? Watch this trick. You'll do this a lot. Think about your numerator. Let's talk about algebra for a second. What I did in the last problem was multiply this through. And you can do that, multiply this through. But look at this 2x that's common to these two terms. If you can think of those as these two terms, and here's an algebra you can do, is factor out the common factor of 2x. And what does that leave you with? Leave you with that. And then minus this thing, which you'd have to distribute the negative. So it's x squared minus 1 all over x squared minus 4 squared, which is equal to x squared minus x squared is nothing, and negative 4 minus 5 is, or negative 4 minus 1 is negative 5 times 2x. So it's this times just negative 5, which is negative 10x. Since I'm running out of room, I should do that extra step probably, but let's say we multiply those over x squared minus 4 quantity squared. Okay, and if I were to graph that, I need to find the slope of the tangent line. So we're not done yet. I gotta plug a 3 in. I get negative 30 over, what is that, 9 minus 4 squared, which is negative 30 over What's 9 minus 4? That's 5. 5 squared is 25. So negative 6/5 is my slope. And now I just need to find the y-intercept. So let's do that. Y equals mx plus b, negative 6/5 x plus b. Plug in your point. 2 comma or 3 comma 2, 3 in x, y in 2, and then solve that for b. Okay, so that's going to be, got some algebra to do here. Negative 18 this plus b is equal to 2, and then I add 18 fifths to 10 fifths, and I get 28 fifths. B equals 28 fifths. All right, so that is my final answer, 28 fifths. And I'm done. And if we take a look at the graph, you can graph this on Desmos. Here's my rational function. And that's that tangent line. I just got negative 6/5 plus 28 fifths, which should be tangent at 3, 2. Okay, let's do one more. Low, D high. So let's just do it this time. That's going to be, bring down the 5 halves, take 1 away. So that's 5 halves minus 2 halves. So that's 3 halves. Low D high minus high D low. Derivative of 2x squared is 4x. Derivative of 4 is 0. All over the denominator squared. Calculus is done. Now for algebra. What can we factor out of this? Okay, this is a good one too. This is a good one to get in the practice of simplifying these. What's common to these? Well, I guess I could do, there's a couple things I can do with it. There's an x to some power I can take out of that. I think before I do the factoring step, I probably better clean it up a little bit. Let's see, 3 times 5 halves is 15 halves. X to the 3 halves times this guy, 2x squared plus 4. And then I guess I can multiply these. That's 2 halves, right? X to the first. So it'd be 7 halves. 12x to the 7 halves. All over 2x squared plus 4 squared. And now, I could have done it up there, but now maybe I kind of prefer to do it this way. What's common to that? You're going to see this a bunch with these. It's x to what power could I factor out of there? Well, it's always the lowest power, right? If like I wanted to factor out a common factor of these two guys, then I'd factor out what? X to the lowest power. And that's what I'm going to do here, the lowest power being x to the 3 halves. And that leaves me 15 halves. That got factored out. 2x squared plus 14 minus 12 to what? X to what power? So you say, okay, 3 halves times what power gives you 7 halves? Well, it'd have to be 4 halves, right? Because you'd be adding, or 2. And this will happen, and now we have a common factor, or we can do some simplification here. A lot of algebra in this problem. Okay, so what I could do is, there's a couple things I could factor out of 1/2. Let's do that. If I factor out of 1/2, this becomes 15. And 1/2 times what is 12? That would have to be 24. And then finally, I can run this through and combine 30x squared minus 24x squared, which is 6x squared, plus 210, 15 times 14, 1/2 x to the 3 halves, and that's all divided by 2x squared plus 4 squared.